This video will be about radiotelemetry. We'll discuss what it is, why we do it, and how we do it. Telemetry is the act of applying physics and trigonometry to find our research animal. We're listening for the signal being emitted from a transmitter that's attached to our research animal. It involves subjective interpretation, so there is artful skill involved as well. There are two basic kinds of telemetry: DHF antenna or GPS satellites. They work similarly in nature. What we do is place a transmitter on our animal, then release it so it can reassimilate in its habitat. Later, we triangulate across the landscape to determine our animal's location. So why do we care where the animals are located? We may want to learn what parts of the habitat are being used by certain species, the timing of use, habitat size, daily movement, dispersal patterns, how much space is required, migration patterns, relationships with others. We may want to monitor disease spread, and much more. We don't go through all this effort to trap the animal and fit it with a collar and triangulate its location to learn where it is. We don't go through all this effort just once. We pursue obtaining hundreds or thousands of locations, all depending on the project. From all those locations, we may want to calculate an individual's 50 or 90% kernel home range, the area in which they spend their time. We do this for many individuals in the population, so we can make inferences about the population. Or we may want to create the MCP home range, the full area the animal is using. Think of it like connecting the outermost locations or the outermost dots. So how do we do radiotelemetry? Remember, we have two basic types, VHF and GPS. VHF is very high frequency. A specific signal is sent from the transmitter placed in the animal, and that signal is received through the antenna. We can receive the data while holding the antenna, while we walk, or while we drive, or while we fly. We travel to multiple locations in order to triangulate and determine each location. The other kind of telemetry is GPS, Global Positioning System. Those collars are using satellites that are already positioned in multiple locations, and a software program triangulates to determine the animal's position at preset intervals, anytime, day or night, meaning you don't have to pay the salary and gas for multiple team members to travel to all those hundreds or thousands of points. Both methods have their own pros and cons, mostly dealing with cost of the equipment, cost of personnel time, battery life, and battery weight. GPS satellite collars' lifespan is shorter than VHF. Their costs are much higher than VHF, but VHF is the most time-consuming, while it's the least expensive to purchase up front. VHF does have longer lifespan and is usually lighter weight. The decision of which technology being used is made by the researcher or project manager, but I truly believe it behooves students to learn VHF, aka the low-tech method, because many wildlife management agencies still use VHF because they already own that infrastructure. Plus, it's the only technology that can be used for certain small species due to the lighter weight batteries involved. That is until technology improves to make collars and batteries lighter weight and longer lasting. Until then, I highly recommend learning VHF and triangulating. No matter which method you use, VHF or GPS, you want to estimate your error polygon. If you do each step correctly, your error polygon is the area where your animal is located. An error polygon is formed when the vectors intersect. Each vector starts at a waypoint, so a specific latitude and longitude on a map, and extends in the direction of your bearing. The bearing is the direction where the strongest signal is coming off of north. You record your waypoint and bearing in the field. To find the bearing, you spin 360 degrees to find the direction from north where you hear that strongest signal coming from. The more waypoints and bearings you take, the better the result, meaning the more confident we can be in the estimated location. In this example, the yellow circles are the waypoints, and the vectors are the dotted yellow lines, and they converge in the red oval. That's our error polygon. The red oval is where we believe our animal is located. DHF telemetry requires a transmitter, a receiver, antenna, a coax cable, a compass, and a map. Think of it like listening to your favorite radio station. It starts with the radio station transmitting sound from a specific location or address. If you want to hear its music, the sound being broadcasted, you turn your radio or your receiver to that unique frequency so that your radio matches the frequency being transmitted. What we do as wildlife biologists is capture an animal, place a radio transmitter on it. We may either glue it directly to its skin or attach it to a collar or a backpack. It all depends on the size and shape of the animal. Then we turn our receiver with the antenna and dial in the same frequency so we can hear the sound being emitted from that animal's transmitter. The antenna we use is directional, meaning we can hear stronger sounds coming from a certain direction. As we change the antenna's direction away from where the sound is being transmitted, we'll hear the signal get weaker. It will get stronger if we're positioned to listen for it in the same direction it's coming from. If we listen for the direction of the strongest signal from multiple locations, then we can determine the animal's location. It requires moving around the landscape to record multiple waypoints or locations, and record bearings, the direction to the strongest signal. Trying to collect these data from many points at the same time and from many points at different times. If we're using DHF technology, we need to know how to use a map and compass. If we're using GPS technology, then the software program does the triangulating for us using satellites. With either method, there is subjective interpretation involved. And we are human and therefore biased, so there is inherent bias involved. We can account for and correct for that bias by testing for user error, by setting our radio transmitter at known locations and testing our method to see how far off we are. First, turn on your receiver and set it to the unique frequency from your animal's transmitter. Record your waypoint, your latitude and longitude. Slowly spin 360 degrees with your antenna up high and parallel to the ground to find the strongest signal. Using a compass, record your bearing that angle towards the strongest signal off of north. Let's watch this in action. All right, so we've dialed in our frequency. Now we're going to spin 360 degrees to listen for the direction where the strongest signal is coming from. You could get louder or stronger. And it seems like it's getting strongest in this direction. So now we take our bearings. So we use the mirror. We keep our compass level. We first rotate our compass so that the red magnet, the magnetic needle, we want it to be aiming to the top where north is. So we move our dial so that north is at the top, so 0 degrees, and we spin our compass until red is in the shed, or that red magnetic needle is in the thick red arrow that aims towards north. So this is north. Our signal is coming in this direction. So if we know that's north, now we're going to spin in that direction. And again, now we're going to turn the dial so that red is in the shed, and then we'll take our reading. And I'm seeing it around 82 degrees is the number that I now see at the top of my compass. So 82 degrees is the first bearing associated with our first waypoint, which happens to be first base. Now we're going to go to 2 more locations. So I mentioned you want to repeat this process at least 2 more times in order to be able to triangulate, form that error polygon to find where our animal is located. I recommend at least 2 more times. And when you're in an urban environment with lots of buildings, you may have bounce back. So the echo, if you will, of the signal. So you may have a strong direction and 180 degrees. You may also have a strong direction of sound. So you want to repeat this process even more times in urban areas because you need to account for bounce back. And the more locations you go to, the more accurate your results are going to be. So I mentioned our last step is going to be triangulating, extending those vectors until they form your error polygon. So let's see that in action. All right, so now let's triangulate. To do that, you'll need to know the latitude and longitude of every location, and you'll need to note your bearing. So let's put our compass at our first location. And I found 82 degrees was the first bearing, so I find 82 on the compass and extend that vector. Now I move the compass over to the second location. And I found that bearing was 62 degrees. So I find 62 degrees on the compass and extend that vector. And now I find our third location, put the compass over that. And I found 8 degrees for that bearing. 8 degrees on the compass and extend that vector. Now I will remove the compass and you'll see this polygon is the location where our animal would be. And it does include home plate, so we were correct with our triangulation skills. Great job. Here's a graphic showing that GPS satellites use a similar concept of forming an error polygon using satellites that are already in different positions to triangulate and locate the animal. Those triangulated locations can be stored on the collar itself or emailed to the user. It's very convenient because a software program does the triangulating instead of the user. But remember that costs are higher and battery life isn't as long, and this can't be done yet on small research animals. So it's still very important to learn VHF methods.